Okay, so let's see. Today we are starting with radial columns. So if we could quickly look at this image again, you can see actually it's not so dissimilar from where we ended off last time with the flag building. Maybe because the crop is a little bit closer, it made it a little bit harder to recognize. But essentially what you have here is a lot of pipes kind of intersecting at a point and then a Boolean operation in the form of a cylinder, right, happening around it. So let's see how we can set that up in our Grasshopper canvas and workspace. And I guess just get started. Okay. So with this type of project, I think, again, we already kind of listed out the different steps that we might take. And so I'm going to use an orient or a transformation, right? So we haven't used really any of these kind of transformations yet. So I think today would be a good time for us to get into that. So I'm going to go ahead and just pull my orient component out, right? And you can see that, it takes three inputs, right? The geometry input, a source input, as well as a target, right? So what this component will do is essentially reposition any piece of geometry that you give it, right? So if I, for instance, created a pipe, right? And then, it would take the pipe from an existing orientation and copy it to a target orientation, right? So in this case, our source and target. So in our example, our geometry will probably start off with a circle first, and then we're going to extrude that to create a pipe towards a point, right? So our geometry can just be, I guess, a circle. So we'll go to our curves tab, go under primitives, find our circle component. And again, if I wanted more choices in terms of how I generated that circle, I could come under here, but I don't think it's that important for this exercise. So we're just going to go with the default circle. And we can see that with the default circle, the expectation is that, again, we'll give it a plane, right? Which is a location in space plus an orientation, right? As well as define a radius, right? So I'm going to go ahead and just connect this circle to my geometry input on the orient component, right? And then, kind of just define this circle a little bit, right? So one thing is I'm going to set up a slider first, a number slider, so that I have some ability to control the scale of that circle, right? Of course, I may need to come back and change the slider later on, but for now, the fact that it's there is just enough for me to, know that there's flexibility in my definition at that point, right? So now the default plane, if we hover over here, we can see it's world XY, right? And I'm tempted to just leave that the way it is for now, but if we need to redefine a plane after that, we could come under our vector tab, right? And choose, whatever other plane that we wanted to use, right? But I think maybe we can get away with not messing with that and just leaving it at its default setting for the time being, right? So now that that's set, I also need to define a source and a target, right? Now, the source here is actually going to be this world XY, right? Which is telling this component that I'm going to use the center, right, of this circle on the world XY as my reference point. So it knows what that is, right? Now, in order to define this, I mean, by default, it already is set to world XY, and this one is set to world XY too. So that's fine. But in this instance, actually, now that they're here, I prefer to actually, have something connected to it so that later on when I'm looking at the definition, or if I were to give this definition to someone else to work on, right? they could see very clearly that, okay, so these two are referencing the same, world XY plane here. Instead of having to come into the components, separate components, and try to figure out and find, what that reference point is, right? So, this wasn't entirely necessary, but I think it's just more clear for anybody who happens to come across this definition. There have been many times, I think, when I've done something and I've come back to it, a year later or something, just because I wanted some functionality. But then, if I didn't set it up in this way, then I'd have to, kind of dive into each component and try to refigure out that logic. And in this case, it's not that difficult, but when your definition gets much, much more complicated, then it's kind of annoying to have to kind of try to figure out and find where, certain things are, right? So it's better, I think, for legibility in a lot of ways to just put it out there, right? Okay, so now we've already pretty much set up everything we need, right? Except we need to tell it, where do I want to orient that geometry onto, right? And so that's our target, right? And we need to define a plane. Now, if we were to define a plane manually, right, we could do that as well, right? We could say, I wanted to move it to, a different plane here, this plane, right? And you can see that, it changed the orientation from being on the XY plane to on the XZ plane, right? In the green circle here. But actually what we really want to do is to create a list of targets, right? So that it can do this many, many times or multiple times very efficiently and very quickly for us, right? And one way to do that, or one way to define targets, right, is to reference them to geometry, right? So, if you remember in our previous example when we were working on the flag building, let me, on the flag building, right, we had a sphere that we subdivided, right, to create these kind of boxes, right, that we extruded to the center. We can use a similar strategy in this case, right? But instead of using the boxes themselves, now we want to use a different profile, basically a circular profile. And, those boxes wouldn't allow us to do that. However, because they're there, right, and they have a orientation, right, we can extract that orientation data from it, right, and use that as our targets, right? So that's what we're going to do now. So we're going to go ahead and create another sphere, just like we did in the previous example, right? A sphere. And then we'll make it a little bit bigger. Let's 10 for now and see how it goes. And the base here again is world XY, right? So there's our sphere. And last time we used a subdivision, right? And again, whenever we're trying to modify the geometry that we have, we go into the geometry type and then look for the utilities tab, right? So here we have a number. Last time I think we used our isotrim, right, to actually cut that sphere into pieces. In this case, we could do that and then use like an analysis on each of those cut panels to find the orientation, right? Evaluate surface. However, it would be quicker in our case this time to simply use surface frames, right? So what this will do is it will generate panels on the surface, right? In that we can define in UV count, right? So if I take this sphere and I connect it, you can see that it's already generating, and that's a little bit hard to see because there's too many. So I'm just gonna, let's reduce that so I can show that to you guys clearly. Oops. Let's reduce the U and the V together to like 3, right? So you can see what that does is that it's, more or less the same. It's dividing up that sphere into, 3 in the U direction and 3 in the V direction. Maybe a bit more would be more clear, right? 4, right? And in doing so, it's finding a kind of point of intersection, right? And from there, creating a perpendicular frame, right? Or plane in this case at that location, right? So the orientation is already correct, right? So the great thing about that is that, well, it's essentially doing the task that we did before without having to, actually generate the geometry and then extract a direction from it, right? Using our evaluate surface component, right? We can just use these frames and assign these frames as our target. So once you've assigned the target, you can see that what it did is that it copied, right, this circle that was down here in the middle, right, several times, right? 1, 2, 3, 4, 5, 6, whatever, right? Every time that there was that kind of UV intersection. And if I increase our UV count, right, the density of that population increases too, right, on that surface. So this is an easy strategy for basically moving lots and lots of geometries onto any surface that you generate, right? To use this kind of orient strategy. So once we have those kind of circles in place, right? What we probably want to do is, I'm going to go ahead and hide some of this stuff so it's not, right? Once we have all those kind of circles in place, maybe we want to modify the pattern, right? Because as it stands, right, if we do it this way, then, we might run into a situation where people can recognize that pattern very clearly, right? Because it's so linear, right? So there's a number of ways to address that. I think last time we talked a little bit about using the kind of lists, right? Sequences, right? Culling things from our list. And so that's a very useful strategy. And I think, just for the sake of convenience, now we're going to use our random reduce, right? To take away some of these circles, right? And do it in a non-predictable way. And I guess if we follow the same logic as last time, right? And we want to keep the whole thing, this whole relationship parametric, then we should use a kind of reduction factor here, right? Instead of a reduction number, right? So if you remember in our last discussion, if we have like 100 items here because we have 10 in the U and the 10 in the V, right? We don't want it to be, we don't want the definition to end up in a situation where if I change this value, then, the functionality here afterwards gets broken, right? So it's better to kind of link those things together by using a kind of defining a percentage or something, and instead of a physical number, right? So a lot of times if you see things that require a number, you may want to modify it by just using some of our mathematical components, right? And let's say I use a number slider again from 0 to 1. And I multiply the number of frames that are here. So I'm going to go to set list, use the list length component to find the number, right? Oops, not parameters. The number here. And okay, something to be clear about here. When we do this, you can see that actually it's repeating 11, 11, 11 as a result, right? 10 times or 11 times, right? And if you remember when we were in our first session, when we were talking about interfaces and stuff like that, and I told you that you could turn on this draw fancy wires thing, right? What that is, again, is because of the structure of the data that's being passed, right? So again, that line is like basic single list, right, being passed through, right? And this kind of dotted line means that multiple lists, right, are being passed through, right? We don't know exactly what happened within this component because we didn't write the component ourselves. But what we can see after we export the data is that we know that, well, that all the data generated from that component came out in kind of separate lists, right? So because they're separate lists, what that means is that when we do our list length, right, to calculate how many items are being sent out, we're not getting the result that we expect, right? And what do we expect? We expect basically like 100 or something like that because we're doing 10 by 10, right? And instead it's returning 11 lists with 11 items each or something like that. So to resolve that, we'll need to use in our sets trees, our flattened tree, right? Now, we're not going to talk too much about this right now because we'll talk about this in more detail when we get to our data management and lists and stuff like that. But just look at the difference between the kind of before and after in terms of what's happening to actually, sorry, I need to connect this one first here, then connect this one here. So, yep. So I'm flattening that all of the data into a single list, right? Then setting that data into the list length to be measured. And that way it's actually measuring all the individual items, right? Instead of a breakdown of the list and then how many items on each list, right? So just know that these tools are available in your sets and trees section, but we will talk about that again, in probably a week or two, right? And that allows us to get this value 121, right? Which if we then multiply by a percentile, we can use our percentile as our reduction factor, right? And if I hide these ones now, so here's the tricky thing, and this is data matching issue, which again is something that we're going to talk about next time. I probably shouldn't just shouldn't have talked about this in this lecture. I should have just waited till next time. But I was feeding it one level of data, the same component, right? I fed it one level of data here and then a different style of data on the top, right? And so I got a result that was fairly unexpected. And we'll look at that more when we talk about data matching. But for now, just know that you generally, need to, you most of the time, you'll want the structure to be the same when you're entering the same component. Not 100% the case. Sometimes there are exceptions and you're looking for a specific type of effect. But in most cases, I think for what you're trying to do, most likely you're going to want to try to keep them the same in the same hierarchy, right? So, lists and lists together, or lists with one single list with certain data, together. And so now you can see this reduction factor will work correctly, right? So if we, have a reduction factor of 1 versus 0, right? We're getting, a fairly random result, right? And again, if we don't like our random result, we're free to use the seed input to change, right, the seed to something that we like. Now, so that gets us, if we look at our geometry here, right, what we're looking to do is actually create pipes that run to a center point now, right? So if we use these circles and we want to make pipes, we're going to go to our surface, freeform, And we're going to look for the component that allows us to make a pipe, right? And that would be this one here, pipe. Now, the pipe kind of requires, oh, am I going to use a pipe or am I going to use a different component here? Maybe because I'm using, not generating lines, but I'm generating circles. Instead of using pipe, I'm going to use freeform and extrude, right? And so I want to extrude these circles to what direction? A center point, right? Now, if I know if we were to do this now, let's see, direction, no direction. And the direction I want is basically here. That would be down, actually. So I need to create a vector and a point at 0, 0, 0. Oh, but it doesn't want a point. Okay, so I actually need to build here another line to the center of that geometry first, right? So what I will do is open this up a little bit so I have a little space here. And what I'm interested in is to kind of create a line from the center of this circle to the center of this sphere, right? So again, if we wanted to find the center of those items, right, get information from them, basically, the circle, we would go under curves, we go under analysis, and we can find, say, actually, we can use surface, and we can do area, find the centroid, and we could do volume to find the center of that volume, right? Then we could use a line, the start and an end point. Oops, point. But that's only the original one. What I want, this one here. Actually, the one that's already been oriented and reduced. Oops. There we go, right? Because I don't need, all of them to have that line. I just need the ones that I want to keep in my design, right? So from here, I can use this line as my direction, I think. There we go, right? To extrude. And you can see they're all coming down to the middle here, right? However, it says there are 34 locally defined values and they're all untrimmed surfaces, right? And I know that the next step for me is going to be to kind of create a cylinder and use it as a cutting object. And if I want to use those Boolean operations, I still need this to be a solid object, right? So I'm going to go to my surface utility and cap, right? So I can cap all of them. I'm going to hide again. Yep. Okay. So that now I have closed breadths, right? Instead of untrimmed surfaces. And then from there, it's simply a matter of making a primitive, right? My cylinder primitive, which can have its base here. That's fine, right? The radius is something I want to be able to define. So I'm going to just put something in there for now. That's quite big, but we can adjust it. Length as well. Now, the length will probably only go in one direction upwards, right? So what I think we'll need to do is actually change the base to a negative value, right? So it can be, or we can just move the cylinder down, right? So let's go ahead and use our transform, move, geometry, motion with the vector in the negative z direction, right? So if I want to make that negative, I can go to my math and I can choose a negative component so that the value is always reversed. And I can just copy this probably. So I moved it down 10 and it's 10 tall. This one, I think I need to change the range to something larger. So set a 0 to that. Adjust the radius. But I don't want to mistake this. Looks like something like that might be about right. Maybe a little bit narrower. I think so. And a little bit shorter. Like that. That looks pretty good. But now before I actually do the Boolean operation again, this one is in solid geometry, untrimmed surfaces. So I'm going to cap those as well under surface utility cap. Hide. And then those will be the ones that I use to do my intersect. And yes, solid intersection, because I want to find what's contained by both, right? So if I hide this, you can see that I'm left with this, right? Which hopefully, if I bake it out into my Rhino window and then hide this, we can look at it a little bit more clearly. Right, is this geometry. So it's an approximation basically of what we're seeing here, right? Using a, parametric process basically. And now, while I bake this one out, we can still hopefully make some modifications to it. See that. Because we took the extra time, right, to make sure that the parametric relationship here on the random reduction didn't affect the connection between the front half of the definition and the second half of the definition, right? Okay, so that's our first example for the day. We have 4 left to go, so I won't dwell too long on that. Please try that on your own, and we'll move on to the next example. Okay, so moving on to the next example. So we should be looking at build program. However, I think I'm going to skip it because, well, I never really liked this example. I don't think it's very useful. So I'll probably end up just removing it from the course in the future, but we'll move ahead to the next one called floor round, right? So with floor round, really, I think one of the key things about this type of geometry is the recognition of the kind of pattern or organization, right? So a lot of times when you see things that have some kind of matrix or a grid or something like that, it's an indicator to you that you're going to probably be using one of these kind of arrays, right? So in our transform tab, we also have things like a box array, a curve array, linear array, polar array, etc., etc. And they work, more or less the same way they did in Rhino, right? So if you remember from our Rhino experience, right, in order to generate this, all we did was, kind of make a simple rectangle or brick, right? Rotate it in space to give it that angle, and then use the array function to create a sweep, right? Of course, using Rhino in a direct modeling method, we're not really able to kind of predict or visualize, right? So we can't, like, for instance, see what this intersection is going to look like before we actually execute, right? Do we want, more distance between the center and the outside, or how many times do we want it to iterate, right? All of those things were, kind of left to experimentation, right? We had to try it. If it didn't look good, we tried it again and tried it again and tried it and tried it again, right? So this is a kind of key example of where setting up a parametric relationship really is beneficial, right? Because it's simple to set up and it allows you to visualize in real time all those different parameters that we're talking about, right? And the effects they have on the overall form and geometry. So, like we've been doing in the past, the first thing that we kind of do is try to conceptualize that process, right? And, if we built it already, then we know the process, which is to first generate that geometry, right? So if we go under our surface tab, we'll be able to come under, say, primitive, right? And find one of these, basically the box tools, right? That'll easily allow us to generate the box that we're looking for, right? And in this case, I think the center box is probably, the one that I would go for, right? Because it allows us to define, the box as a location, right? As well as basically the 3 dimensions of that box, right? So let's go ahead and use sliders to do that. And I'm going to set up some sliders, integer sliders. And I want to be able to control those independently of each other. So I'm going to set it up. I won't link them all to the same slider in this case. Okay. So it looks like, we probably don't need 10. Maybe 1 is enough in the Z. And let's start with like 5 or maybe even smaller. 4, 3. Start with 3 and see how it goes. That's our unit, right? Our brick, basically. Now, if you remember when we built that geometry in Rhino, before we did the actual array, right? We kind of played around with the rotation of that brick, right? So to do that, we can, either move it, do that transformation afterwards, or in this case, because we have ability to define a base, right? And it's currently defined as world XY, we could just change the plane, right? To something that we want to use, right? And in this case, we can, let's say we use a transform and we use a rotate, right? Under the Euclidean transformations. And we use that so that we're actually rotating the plane in which we want the box to be generated on, right? And so here, the geometry that we're going to use is going to be a plane that we define in space using the world XY, right? And we will change the angle, right? Now, one thing about angles in Grasshopper is they're all typically defined in radians, right? I don't know how you guys are with radians. I don't think in radians, right? So the first thing I always do whenever I see any angle is I change it to degrees, right? So unless you're so I just came here, right click, and I use the pop-up menu to change that to degrees. If you guys are comfortable working in radians, you can do that all day. It's up to you. But there are times when maybe it's useful for you to right click into some of these inputs because they may offer you some other options such as this, right? And later on when we talk about flattening and grafting and stuff like that, the data management stuff, right, this right click menu will be more and more useful, right? So now you can see here, if I set like a slider that has 1,000 degrees of rotation, right, I'm able to very easily control that rotation angle by changing the plane, right, that the box gets constructed on, right? Okay, so from there, we also have a rotation plane. And with that rotation plane, it's going to be the plane that we're rotating in addition to the XY rotation, right? And in that case, we're probably going to choose the YZ or the XZ. Which direction are we choosing? If this is the XZ, XZ, the XZ, XZ, XZ plane. Right. So all that, because the direction in which because we didn't define the direction that we wanted to rotate in, right? We just said the geometry is here. So by default, it was on the same plane, the world XY, right? But that means it's just kind of spinning around itself, which is not going to be very useful for us because in our example here, right, what we see is that the rotation is actually happening in a different plane, right? And in this case, I've set it to rotate in the XY plane. And so that looks like it's now moving in the correct direction. Okay, so our base is set up, right? Now, the next step is to actually do the array, right? So if we go back to our transform tab and we choose our array, in this case, because we can see that it's circular, right? We're going to choose a polar array. And we're going to use the geometry. And right away, you can see already that it's doing something, right? So there's the plane, there's the count, as well as the angle. So in this case, the angle is defaulted at 360, right? But we can do the same thing that we did here at the other one, is we can change this angle to a degree, use a slider to decide on a count number too. I don't think we need something so high as we, oops. I guess the limit is probably 100 in this case. So you can see if I increase the number, right, we get more objects. And if I change the rotation, we have more or less rotation, right? But what's happening is that everything is happening around this point in space, right? So we have a couple options in which we can deal with it. And one is to change the location of this polar array, this plane, right? Essentially the center point that you want it to be rotated around. If we offset that in any direction, right, then that will change the appearance of that circle. But we can also move this from away from the origin, right, and use that as a strategy for actually creating that distance that we need for the circle to appear, right? So why don't we do that since we're already on the transform tab here? Let's just take this geometry first and use that as the input geometry. and have our motion not be in the Z direction, let's reset that direction to, let's say, Y. And by a factor of, let's use this 100 tab slider. So you can see what this does is that it increases the distance, right, between the center point, right, and where that array occurs, right? This changes the rotation, right? So with less rotation, you have the same number of count, right, being iterated through space more or less times, right? Now, if I wanted to make that more clear, I could increase the number of count to say something a little bit higher. Maybe that's less clear. Say something like that, because we know we want some degree of overlapping between each geometry, right? We look at our image again there. And then we can come back to our angle of rotation and adjust that, right? Create more the effect that we're looking for, right? And again, all of these things we can tweak and modify in real time and see the result, just to get an idea of what we're working with, right? And if you wanted to really match it up to the existing condition, you can come here and you can count it 1, 2, 3, 4, 5, 6, 7, 8, right? And I can come here and I adjust this to 8. Make sure this is 360 so that it's a full revolution. This is now too much space, so I'm going to reduce the space so that we can create that overlapping, right? And then we can adjust this angle till there's a biting in just enough, right? So all of these things are things that we can, and now it appears that, that geometry may be a little bit too thick. So what if I did something like this, right? And then opened it up a little bit, the spacing, right? All of these things are now basically the design parameters, right? Which you can come in and define and modify at the end when you set everything up, right? To get it just right, what you're looking for, right? So again, here, when we're done, we can bake it out into our Rhino environment. Have a quick look to see how it looks. And that looks, I guess, pretty good, right? So that is our floor round. Why don't you guys give that a try, and then we'll move on to the next. Okay, so moving on to the next example here, creeping tower. We can see some similarities between creeping tower and the floor round, right? Which is that, there's kind of a basic module, right? And it getting iterated across a geometry. But in this case, the geometry is more vague, right? And seems to offer a little bit more flexibility and is just more freeform in general. However, the geometry in floor round was more kind of generic, right? And you just had these kind of intersections, whereas with creeping tower, right, you can see that one kind of fits into the next one. And so I think that'll be kind of a little bit trickier part of this example, but a very similar strategy, right? So if we go back to our transform tab, you'll see that under array tools, we have one here called the curve array, right? Which offers, quite a bit more flexibility than these other options. But again, this is something that we'll probably, if you remember from our previous example, we'll probably run into or need at the very end of our definition. But having it here will help us to, begin to think and understand what it is that we need to build up to that final geometry, right? And so if we look at it, you can see that, there's count, there's curve, and there's geometry. And really the two parts that require development are the geometry and the curve, right? So once we figure out those two, the rest should be pretty straightforward. So let's go ahead and work on geometry first and see what we can get there, right? So, in order to get this kind of shape, you can see it's more or less a box, right? Except that, it needs to be tapered so that the one above and the one below, can kind of look like they're fitting into each other, right? It's hollow here. So we're not going to be able to use a straight box like from our surface and primitive, right? Any of these, they're not really going to do the job for us. But instead, we'll probably choose to use something from our freeform, right? We use this one quite a lot already, the extrude to point, right? Because we know that that one will allow us to create a tapered effect, right? However, because we're extruding it to a point in space, it also means that probably, right, it's going to have a sharp end, right? And we're not going to, necessarily be interested in that. So we're going to have to modify the geometry that gets created slightly, right? Okay, so now that we have our extrude to point set up, we need a base geometry and a point for it to extrude to, right? So let's pick our base geometry first. In this example, what I would use, I think, is a maybe surface. Yeah, let's use the plane surface as our starting point, right? So, this one's useful because it allows us to define basically, a flat plane, right? With a X and Y domain. We're interested really in box shapes. So we're going to want to keep these the same, but we need to define that range, right? So we're going to go back to our math tab like we did before, go under domain and use this one called a bounds, right? Oops, sorry, not bounds, range. What is this one? Construct domain. So have a start and an end, right? And so I think if we do, and because I think we're going to have negative numbers here, so maybe I'll just do 10 here and then I'll modify our values so that we can accept negative values as well. And that should allow us to go from negative 10 to positive 10, right? We can adjust those later on. To our requirements. Right? So for now, 10 and 10 is probably okay. And we've defined our plane, right? From there, we're going to use our plane as our base of extrusion, right? And then we want to set up a point or construct a point that will serve as the extrusion point, right? So we go in our curve, actually vector, and we say Z, unit Z. And have a factor here. I'm not sure. I think this will probably need to be higher than that, but we can also instead, tighten our plane to begin with, right? So now we have this kind of tapered shape, but we don't really want the whole thing, right? Like I said, we have to modify it a little bit. So let's go ahead and create a geometry that we can use as a cutting geometry to remove the top part of this extrusion, right? And for that, we're just going to use, I think, a surface and let's say center box. And I'm going to use, actually, is there something easier? A box rectangle. So I need to define a rectangle in this case. Curve, rectangle. Wouldn't it be nice if I could just use this? Yes, it would be. There we go. So I created a box here. I'm not too concerned about what the height is. It can be, kind of whatever it wants to be. because I'm just using it as a cutting object, right? But I do, if I want to cut the top part off, I need to decide how high up to move it before I can use it as a cutting object. So I'm going to go ahead and use transform to move that box in the Z direction by a certain amount, right? So we go to our Z unit vector. And give it a slider to control the factor. Move it into position, something like this looks okay. And then I'm going to go ahead and use our intersect Boolean to cut, right? And I'm going to cut the extruded geometry by this with this geometry and hide this so we can see what we're left with. We're left with this, right? Which is pretty close to one of those modules, except that it's a solid, right? There's no like hole here, right? So in fact, I'm going to take this one, move it again, right? Effectively creating a second copy of it and moving it in the Z direction. However, I want this one to be moved in the negative direction, right? So I'm going to go to my math tab again, use a negative factor, use the slider to actually position it. And I think, something like this is probably good, right? And then I'm going to go ahead and use my intersect again, cutting using this one, cutting with this one, leaving this one, hiding this, right? So there we have it. That's our unit to work with. So we know that we can use this geometry, right? The next thing that we need to define in order to get this to work is the curve, right? So that's pretty straightforward. We just need a curve here. The shape that we're interested in is fairly freeform, right? You can see this kind of got this kind of S curve, right? So that tells me I'm going to want to use a spline, right? And maybe a NURBS curve spline, right? Now, to approach anything close to that type of curvature, we will probably need at least 4 points, right? You can use as many or as few points as you like, but, for the sake of this example, we're just going to use 4. So I'm going to construct points very simply, just by using the construct point component, right? And then an X, Y, and Z for each one. In reality, you probably never really build a curve in this way because it's not very efficient to go, point by point for every curve that you're trying to make. Normally, these points may be generated or derived from some other geometry that you're working with, right? But for this example here, since, we don't really have anything else to build off from, we'll just stick to manually generating that curve, right? Instead of extracting it from something. So we said we need to construct at least 4 points. This is just 1 point in space now, right? So I'm going to make 4 sets of these just by copying them. And then, kind of move them around. So if this is my first point, right? And then my last point, let's just put this, max them out for the last one. And then have the others kind of somewhere in between, right? I don't know exactly, where that's going to take us yet. But, basically we have a curve kind of like this, right? And the order here matters, right? So the first point that you put in will, be the first point that gets generated, right? and I'm holding shift to put them all in. And you can see here that already, right? Just by setting that curve up and doing it in this way, you're already getting a translation, right, of that geometry, right? Okay, so from there, the last component that we have is simply a count. So let's say, I don't know, 20. Modify the number, right, that we're going to have in our example. Now, let's see what happens if we start moving this around. So I think this geometry is currently too big for the size of this curve. So in a way, these are all too close, and therefore, when these got arrayed, they're not arraying and orienting, quite to the point where we want them to be. And they're doing so at the wrong location in relationship to our geometry, right? So if I were to move this to here and limit these guys to values that are above a certain range, then I think that would actually work out a little bit better. What else can I do to make this smaller? Let's start to modify this. You can see as I start to modify them, they start to adjust a little bit, and we can kind of find a sweet spot for how far apart they get and what works best. I think essentially the range that we set up this curve originally was a little bit too small. Like if these values had all been, in the 20s or 30s instead of between 1 and 10, probably would have had more flexibility in terms of how we can set up this geometry and have this kind of overlap look correct. But, it's okay. We kind of adjusted it a little bit and it looks not too bad, I guess. Not great, but it's okay. For the purposes of this example, it's fine. Okay, so hide the stuff that we're not interested in. Bake the geometry. So we could take a look at it inside Rhino. And yeah, I mean, it's okay, right? There's a little bit of work can be done there. But again, I think if the proportions in terms of the size of this box, right? And the length of our line were a little bit better, right? Longer line length and smaller box. Probably would have worked just, a little bit nicer, right? But I'll let you guys play around with that on your own, right? This is overall the strategy that you would take to get something like this creeping tower here. Yeah. Okay, so with that, let's move on to our final example for the day. Okay, so in the final example for today, we're looking at this one called bundled tower, right? So if we think back to how we modeled this in our Rhino class, basically what we did was we generated 4 sets of squares, right, in a matrix, and then we lofted down across to get this kind of tubes, right? And we kind of changed the scale of those sets and stuff like that. So we'll approach this one with a similar strategy. So the first thing we'd want to do is to go and set up that matrix or grid, right? So if we go to our transform tool again, you can see that we have this rectangular array. Oh, that's small. So I think we'll probably start from here, right? Now with this one, you can see that by default, there's 6 and 3, right? And the cell has a set size of width of 10 and h of 5 and no base geometry. So, okay. Let's go ahead and define these things manually first. I'm going to use a slider for the X and the Y. I think probably we could, since we're working with something that's proportionally square, it should be fine for us to use 1 to control both the X and the Y. For the cell itself, I think maybe we can go and define the geometry for that, right? So let's use a rectangle in this case. I think I'm going to go to our primitives here and choose a rectangle component. In this case, we're more interested in curves and surfaces, right? Because we know that eventually down the line, what we're going to try to do is use a loft command, right? And that loft command will take curves as well, right? So it wouldn't make sense for us to, use a surface geometry to make that rectangle or a plane, right? Like we did in the previous example, because it made sense in that case because in those cases, we're looking at creating solid geometry, and the tool that we're using to was the Boolean operation, basically, right? So it's even though this is a step-by-step thing, right? Knowing the capabilities and what tools you're going to use from the beginning to end can help you to make better decisions in the beginning of your definition, basically, right? Okay, so I'm going to go ahead and start by creating a rectangle, and I think the size, let's keep it small for now. I'm going to go ahead and use a slider for that as well, but I'm just going to set them to 1. And again, because primarily everything we're working with here in this example is going to be square, I think it's fine again to use a single slider, control both of these, right? And then from there, I'm not going to define a radius because, I'd like them to have sharp edges, and the plane will accept the world XY, right? So that rectangle we'll use as our geometry here, right? And we'll set up another one, a second one, as our cell. And you'll see why in a second. So when I connect this and I highlight, you can see that basically, if I have this both set to 1, right, the boxes that are generated are more or less, 4 and 4 and then right next to each other, right? But the cell is what controls the distance in between, right? So, you can go from, and the geometry is the size of the box itself, right? So you can think about it in that way. The cell, is the size of the overall organization, and then the box is just for that component itself, right? Okay, so we've started that first process, right? Now, in our example, we'll need 4 instances of this, right? To loft from bottom to top. Because if we look back at our image, we know that we'll need something to define the top layer. We'll need something to define this middle, and then this bottom here, right? So at least 4. Now, normally, right, if we were going to make 4 instances, we could just use the move and copy and paste, right? But in this case, because we actually need each of those 4 instances will be slightly different probably. So in this case, I'm just going to repeat this for all of them, right? Or, create 4 that, 4 sets of this with different values, right? Now, I probably don't need to redo all of these. I probably only need to set these up. So let me move this away for the moment and then make copies of that. So now I have 4 sets of 4 by 4 all on top of each other. Now, question is, okay, how many do I want with what characteristics, right? So if we look at the kind of top and bottom condition in this example, they're kind of spread out more, and then the 2 middle ones are more or less touching, right? So if you remember, if we wanted them to be touching, we need to assign the same box size as the cell size. So in these 2 middle ones, that's what I'm going to do. Instead of connecting the cell to here, I'm going to disconnect those, right? Using the control and deselect. And then I'm going to hold shift and add those to the, this top rectangle set, right? And what that does, if you look at it, is that now we've created, 2 sets where there's space in between, and then 2 sets, where they're all next to each other, right? And that'll give us that variety that we're looking for. Now, the next thing, right, would be to position those 4 layers in space vertically, right, in the z-axis. So we can use a move, right, from our transformation here. And we're going to do our motion restrict it to the z direction by a certain factor, right? I'm not sure what I'm going to need at this point. I'm just going to say 20 and see what happens. And I'm going to set that to the geometry to there, right? So you can see I moved this one from here up 20, right? That looks not bad, actually. So I think we're probably working with, in the kind of 0 to 20 range. So I'm going to repeat that in each of these instances as well, right? Replace the geometry in each case. And then change these values. So the top was 20, let's say 15, 10, 0, 7, 13, something like this. I'm going to hide the previous stuff for clarity. And you can see that now we have, essentially our 4 tiers, right? of objects. Now, these two in the middle, because they're all aligned along this edge, right, may not look great there. So I'm going to actually add directionality to the motion on the two middle ones. Instead of just limiting them to the z-axis, we're going to actually define a vector, right? So for these two, I'm going to define a vector with more than one direction, right? So they will have a z component, right? As well as an x and y component. In fact, I'm just going to actually here. So the x and the y component can be identical sliders, right? But I don't know what the values are going to be exactly at this point, right? Probably, not that extreme, I guess. Right, that seems okay. And then it looks like if I copy and paste these two, something like that seems all right. We can do something like that. Okay, so our 4 tiers are set up now, right? That's great. So now we would think, okay, well, I guess the last step is to loft these together, right? So let's see what happens when we try that. We go to our free form and we choose loft, right? You can see that we want input curves, and great, we have curves here, right? 16 locally defined values as rectangles. So if I say, okay, loft that, loft that, loft that, loft this, we didn't get anywhere near the result that we were hoping to, right? And the reason for that is actually, again, this has to do with this concept of data management, right? So the data, as it was coming out from here, right, is rectangle 1 list with the rectangle 0 to 15, right? And if I add, right, a second list, now that list got longer, right? 0 to 31. And I add another list, right? Longer still, 47. And I add another list all the way to 63, right? All in one list, right? So what does that mean? Well, that means that this loft will interpret, right, the data as being a single loft from number 1 all the way to number 63, right? So that's what you see it doing here. It's going lofting from this box. It's lofting from here to here to here to here, then lofting to here to here to here to here, then to here to here to here to here, here, till it gets to this one. And then it goes to the next one on the list, which happens to be this one here, right? And then loft here, here, all the way back, right? And it keeps doing that, right? And the reason for that is simply because of how the data got organized, right? When you put them all together, right? So this indicates a kind of problem for us, right? Because what we wanted to do, right, is to go from here to here to here to here, right? Which is essentially like if we said, okay, so that's right. This is this, right? And I want you to loft 0, 0, 0, 0 together, then loft 1, 1, 1, 1 together, then loft 2, 2, 2, 2 together, 3, 3, 3, 3 together in that direction, right? So how can we do that, right? How can we change the structure of the data that's coming out to something that's useful for us? And again, that's where we would come into our sets tab and look at our list management tools. All right, so here, again, we have these tools that allow us to modify, right, the structure of our list, right? And you can see some of them are for, doing partitioning, some are changing the direction of the list, right? And essentially that's where all of this kind of data management happens, right? So in this case, right, what I want to do is to modify how those lists get broken up, right? And to do that, I'm going to partition it into subparts, right? So what I'm gonna do then is, let's see, maybe this will be more clear for you if I leave one of these up. Right, so originally we had one list with 15 items on it, right? And if I put this into the partition, right? And then I define the partition with a certain size, right? Right now, I think by default, you can see it was set to 3 and 2, right? So the way that that component partitioned that 15 pieces of data is to make separate lists, right? With 3 items, 2 items, 3 items, 2 items, 3 items, 2 items, right? Because that's what we told it to do down here under size, right? So instead of one list with 15 items, you have 1, 2, 3, 4, 5, 7 lists with alternating 3 and 2 items, right? That's not the list that we wanted to create, though. What we wanted to create is actually a list of 1 item each, right? So if I were to just set this size to 1, you could see what happens now is that instead of having one list with 15 items, I have 15 lists with 1 item each, right? And when you do that, what happens is that now instead of the geometry matching up within a list, since there's only 1 item in that list, what it will do is it'll match all the items on the same list, right? So this, if I make a copy of this one, right? Now it would understand, okay, so what you want me to do then is to loft everything that's on this list 000 together, right? So this is on 0002. Everything on 001 together, right? And these two both have values, right? So if you had 10 values, right, everything within that list would get lofted together, right, in that way. So essentially what we're doing, right, is we're going to do that for all of these, right? So that we're telling it, okay, I want you to loft in this direction, right? Now I use this one chunks as an example of how these sets work and what kind of options you have. We'll talk again, this will lead into next week, I think, when we start data management stuff, but there's actually a more simple and straightforward way to do this if all we're thinking to do is to make everything a list of itself, right? And that is to use our graph, right? We saw before, right, how when we use the under tree, we use the flatten, right? And when we flatten the tree, let's just do this. When we flatten the tree, all the items on separate lists became combined onto a single list, right? Essentially, graph does the exact opposite. So here, everything is on one list. I put in that and then output it. and everything becomes its own list, right? So these are opposite functions from one another, right? And they do opposite things. Chunk or partition can also do that, right? But what it lets us do is define a custom size, right? So we can say group two things together, then group one thing together, then group three things together, etc., right? So this offers additional functionality that we don't need in this example, but is good to know, right? So today we will just use our graft, right? And we will graft that data first before inputting it into our loft, right? So you can see that gets us something closer to what we're looking for, right? In this example. Now, the only thing though is that actually we're not really interested in this kind of smooth shape, right? Which is the default for loft geometries. So if we go into freeform loft options, right? We can change our options to change the type, right? So you can see here under type, it has loft type. 0 is normal, 1 is loose, 2 is tight, 3 is straight, and 5 is uniform, right? So you can go, that means we can use, a slider with some number values to define the type of loft that we wanted to create, right? And when I cycle through these, you can see the variations in the different loft types, and it will fail if if it's not able to generate that one. So loft type 3, which should be the straight, right, is the closest option that we have to this example that we have here, which is bundled tower, right? Now, I feel like this can be a little bit further apart, so I'm going to go ahead and move this higher. I'm going to move this a little bit lower, right? Maybe not that much, just one. Yeah. Right? And that more or less gets us to our final result here as well, right? So I'm going to go ahead and bake this into our Rhino environment, hide the definition here, so we can view it quickly in a rendered mode. We didn't cap those off, which is a shame. So let's see if we can do that quickly. Those lofts we cap, then bake, then hide, right? And that should be about it, right? So that looks, similar to what we have in our example here, right? Conceptually. Of course, we can be tweaking these proportions and moving things around a little bit manually if we wanted to, but conceptually, that's, I think, essentially what we're looking at, right? All right, so that concludes the lecture for today. We covered all of our kind of early exercises except for, I guess, radar slab and mill program, which I probably will end up removing anyways because they're not very useful. And next week, when we continue, we'll start looking in more detail about, how to manage data and how data matching works and stuff like that, right? Because as you can probably tell from today's example, this last one that we had, the results that you get are dramatically different simply by changing, the organization of the data that's coming in and out of each component, right? Even though all the components that we were using were the same, if we hadn't changed the data structure at the end, we never have arrived at this solution, right? We would have gotten that, that other weird thing. So I think next 2 weeks will be very important for everybody. I think this is, really data management, and these kind of data concepts are the heart of parametric design. And they're also, unfortunately, the kind of make or break point for a lot of students. I think a lot of students get to this point, and even though they're comfortable working, with the interface, and they know how to model using parametric tools, they never really get a good grasp of how to modify data and how to, control data structure. And so, with that as a limitation, it really kind of hampers your development as a, in parametric design, right? So really those students that do well are people who manage to understand the rationality behind data sets and data structure well. And then, there's the rest of everybody who learns Grasshopper, which is, kind of knows how to use the interface and whatnot, but, get stuck because they can't really control the outcome, right? And so the next 2 weeks are very important. The material will be quite dense. It's not going to be the most exciting thing to look at, but the concepts are crucial. So be sure to check next week's videos, and we'll see you then.